Now we're going to start looking at some graphing situations that get a little bit trickier. We'll explore what's going on at first, and then eventually we'll get to a point where we'll have a step-by-step procedure we can go through to make sure we get things correct. So we're moving on to exercise 5. The next few graphs you can also do in a handout sheet posted in Canvas where I just sort of set up a graph grid, or you can do them on your own graph paper, of course. And I guess in this example, I still have the axes labeled. Eventually, we're going to have to do all the labeling ourselves, or you are going to. But let's go ahead and start working on this graph of y equals sine 2x. The parentheses here are optional. So we often just write this without the parentheses. That's a traditional notation, but I just put parentheses in here to emphasize the fact that the 2 here is inside the function input part, inside the sine function, as opposed to a 2 out in front. Well, let's just go ahead and start checking our quadrantal values here and see what we get for this function. So when x is 0, we get sine of 2 times 0, which is sine of 0, or 0, so we got 0, 0, okay. Sine at pi over 2, we get sine of 2 times pi over 2. The 2's are going to cancel, so we get sine of pi. Sine of pi is 0. At pi, we get sine of 2 times pi, which is just sine of 2 pi, which is 0. Okay, I'm getting a lot of zeros here. This is not good. Sine of 2 times 3 pi over 2 is the 2's will cancel again, so I get sine of 3 pi, which is also 0. Now when I get to 2 pi, sine of 2 times 2 pi is sine of 4 pi, which is like 2 times around the unit circle, which is back to 0. So far on my graph, I have 0, 0, pi over 2, 0, pi 0, 3 pi over 2, 0, and 2 pi 0. I'm just getting a whole bunch of zeros, and now I think you should suspect that for this function, the graph is not just a horizontal line. What we're seeing here is that we can't always rely on the quadrantal angle values to take care of us, that they might not give us enough information to sketch a graph. What we want to find whenever we graph a sine or cosine function, we certainly want to find these zeros, but we also got to find those high points and low points on the wave, right? If we can just find the high and low points on the wave, it won't be hard to sketch the graph. So we'll examine that in a little bit more detail in a minute, but let's just try playing with this one example and look at a few other possible x values. So for instance, halfway in between 0 and pi over 2 is pi over 4, right? That's like 45 degrees. So what happens if I plug in pi over 4 into this function? I get sine of 2 times pi over 4, but sine of 2 pi over 4 is the same as sine of pi over 2, and that's 1. So, aha, we finally got something other than 0 here. If I go up to the graph, at pi over 4, we're 1 unit up. And why don't we try halfway between pi over 2 and pi is 3 pi over 4. Let's try plugging in 3 pi over 4. Sine of 2 times 3 pi over 4 is sine of 6 pi over 4, or sine of 3 pi over 2, which is negative 1. So at 3 pi over 4, I'm away from the x-axis again. I get a point at negative 1. Now, I don't think it's totally obvious yet, but I am going to jump ahead here a little bit. We're getting this kind of shape for our graph. What's happened is one period has been compressed, And we're going through one period of this graph just from x equals 0 to x equals pi, instead of having to go 2 pi full units. And if I check, let's see, let's try 5 pi over 4. If I plug 5 pi over 4 into this function, sine of 2 times 5 pi over 4 is sine of 10 pi over 4, which is sine of 5 pi over 2. Okay, here's where I'm going to rely on my basic sine graph. Sine of 5 pi over 2 we know is 1. So the y value here is 1. And so at 5 pi over 4, I'm back up to 1. I can see this pattern starting to repeat itself, right? So I'm not even going to check at, what would this would be 7 pi over 4. I know I'm going to be at negative 1. At 2 pi, I'm back to the 0. Here, I'm going to be at 1. Halfway between 2 pi and 5 pi over 2. Then back at 0. Halfway in between here, I'll be at negative 1. And even if I go in the negative direction, here's negative pi over 2. And in between is negative pi over 4. So I'm going to go down to negative 1, back to 0, up to 1, back to 0. I know this pattern's going to repeat itself just from the nature of a sine function. So I'm getting a graph of y equals sine x. Now we're going to try, what we want to be able to do is we want to be able to figure out this period change without having to plot a lot of points, right? That's what we're going to look at. But just before we do that, I want to note, so from 0 to pi, that's one period of this graph. The amplitude here, we say is 1, because that's the distance from the x-axis to the top of the graph. So that 2 factor that we see in the expression for the function, it doesn't stretch out the amplitude like some of those previous examples we saw. It compresses the period to a shorter distance. A change in period like this, if this were a sound wave, that would be a change in frequency, right? It would be a different note on the scale. It wouldn't be louder or softer like an amplitude change. It would be a frequency change. And let's also now add the regular sine wave to this picture, like we did in some of those earlier ones. So we'd be 1 at pi over 2, 0 at pi, negative 1 at 3 pi over 2, 0 at 2 pi, 1 at 5 pi over 2, 0 at 3 pi, negative 1 at negative pi over 2, 0 at pi. So just for the record, there's sine x with its usual 2 pi period. So you get a sense of how this wave has been kind of compressed. So how can we spot this? How can we spot this? Well, here's what we're going to be able to do. I'm going to try to sum this up before the end of this video. If we just take sine x, it has period 2 pi, and you can think of that 2 pi period as occurring in the interval when x takes values from 0 to 2 pi. So it's like this x is that x. In general, if I take y equals sine of anything, okay, we're going to get a period by taking an interval of that anything taking values between 0 and 2 pi. In other words, what's written there gets written there. Now let's compare this to y equals sine 2x, the graph we just did, if we're trying to identify its period, I'm going to set up an inequality where I take this 2 pi expression and I can put it in this inequality between, I'm going to take the 2x expression, sorry, and put it in this inequality between 0 and 2 pi. And if I divide by 2 to isolate x, I get 0 less than or equal to x less than or equal to pi. There is the period for y equals sine 2x. I don't know why I'm writing in red now, but I am. And here's the way this works in general. If I take y equals sine of bx, I can take that bx and put it in an equality where I have 0 and 2 pi at each end, and then isolate x by dividing by b, and I get 0 less than or equal to x less than or equal to 2 pi over b. That 2 pi over b is the period. So if you start out with this kind of function, sine equals bx, its period is always going to be given by this formula. Sine is 2 pi over b. And let's see. So we're going to work with this some more, formula some more. And just before we leave this video, I want to go back to the graph, sine 2x. And just, I wanted these two graphs together. I think it's a good comparison of sine 2x and 2 sine x together, exercise 1. Notice the difference between these two and the different effect of the 2 factor involved on the two graphs. And we're going to continue working with period in the next video.